The filter section of Syntronik is the main tone coloring tool of the instrument. This video will explain our approach to the Syntronik filters and provide some tips and insight for how to get the most out of them. In an analog synth, the oscillators generate the sound, and then the oscillators are mixed together and sent into the filter. The filter then does exactly that. It filters the oscillator sound to produce more interesting tones and colors. Syntronik works the same way. Our oscillator section routes straight into the filter. We've already discussed the oscillator section in the previous tutorial video, showing you how to get the most out of that section of Syntronik. If you haven't seen it, please check it out. Once you've set your oscillators the way you want them, the next step is to adjust the filter. All of Syntronik's filters are available in every synth. That means that you can put a Moog-style filter on an Oberheim sound, an Oberheim-style filter on a string synth, a Roland-style filter on a vintage Moog sound, or even a modern Formant filter on an Andromeda sound. First, choose the filter type. Syntronik provides 7 different filter types. The first 4 have been meticulously modeled from carefully maintained vintage analog synthesizer instruments. The M type, based on the famous Bob Moog transistor ladder filter, found in the 904A low-pass filter module, and of course the Minimoog. The R type, based on the Roland IR3109 integrated circuit chip, found in the Jupiter-8 and Juno-60 synths. The C type, based on the Curtis CEM3320 integrated circuit chip, found in the Oberheim OB-Xa, the most common Rev 3 version of the Prophet-5, the PPG Wave 2.3, and many other classic synths. The O type, based on the Oberheim SEM synthesizer expander module. The classic 2-pole state variable filter used in the SEM along with the 2-voice, 4-voice, and monster 8-voice polyphonic systems. Then there are 3 digital filters for a more modern approach. The phaser filter for lush, sweeping, all-pass filter sounds that are reminiscent of classic stomp boxes. But here you can sweep the phaser with more precise control using an envelope or LFO. The Formant filter for human vocal tract resonance. And the classic filter, the original sample tank filter that you've heard in IK instruments for many years, including the original Sample Moog product. The next parameter to adjust is the mode. The mode determines what range of frequencies to filter out. There are 4 filter modes. LP for low pass. The low pass filter cuts high frequencies and lets lows pass through. This is the most common type of synth filter. BP for bandpass. The bandpass filter cuts high and low frequencies to let just a certain band pass through. Bandpass filters are generally thin and edgy sounding because they're cutting both lows and highs, leaving only a range of frequencies in the middle of the spectrum. HP for high pass. The high pass filter cuts low frequencies and lets highs pass through. And Knotch. The Knotch filter is the inverse of the bandpass filter. It cuts, or notches, only a very small frequency range and lets the lows and highs around it pass through. Note that not all modes are available for all filters. For example, the R-type and C-type filters only offer the low-pass mode. Next, set the slope of the filter. The slope determines the number of decibels per octave that the filter cuts. A 12 dB filter, most commonly known from the famous Oberheim SEM filter, the O-type filter in Syntronik, filters frequencies at a medium slope of 12 decibels per octave. A 24 dB filter, most commonly known from the famous Bob Moog transistor ladder filter, the M-type filter in Syntronik, filters frequencies at a steeper slope of 24 decibels per octave. A 6 dB filter is the most subtle sounding filter, filtering frequencies at a gentle 6 decibels per octave. You may have heard the term pole used with filters, as in a 4-pole or a 2-pole filter. A 4-pole filter is the same as a 24 dB per octave filter. A 3-pole filter is the same as an 18 dB per octave filter. 2-pole is the same as a 12 dB per octave filter, and 1-pole is the same as a 6 dB per octave filter. It's just two ways of talking about the same thing. Now the big one, cutoff. The cutoff knob sets the frequency at which the filter will start to cut. If you set the cutoff to 1 kHz with a low-pass filter, it will cut frequencies above 1 kHz. If you set the cutoff to 200 Hz with a high-pass filter, it will cut frequencies below 200 Hz. Move the cutoff knob to set the starting frequency of the filter. Note that the filter cutoff frequency is the synth parameter that gets modulated the most, usually with an envelope, but also with an LFO, key tracking, mod wheel, or any MIDI continuous controller. The filter envelope, with its very important envelope amount control, is another topic that we will discuss in a future video. Next is the resonance control. Resonance sets how much emphasis, or gain, will be put at the filter cutoff frequency. This adds a peaking sound to the filter, especially prominent when the filter is swept. The drive control models analog input overdrive of the filter. On most classic synths, when the oscillator mix was turned up past about 60%, the input of the filter would start to subtly saturate, and this overdrive contributed to the signature sound of those excellent machines. Syntronik models this behavior and provides control over it here with the drive parameter. Lastly, the velocity control lets incoming keyboard velocity modulate the filter cutoff frequency either up or down. Positive velocity values increase the cutoff frequency the harder you play. And negative values decrease the cutoff frequency with harder velocities. Note that some controls change their function depending on which filter type you choose. For example, the phaser filter type changes the slope control to a stages control, so you can select the number of stages in the phaser. It also changes the cutoff control to depth and the resonance control to feedback. In all cases, the controls will be relevant to the filter type you select. As mentioned earlier, the filter cutoff frequency can be modulated by the filter envelope and LFO. We'll talk about those sections next time.